Newton's second law. This week we cover a simple example related to Newton's second law, F equals ma. Let's get started. The simple concept we're covering today is Newton's second law, which is F equals ma. And the more formal textbook definition for Newton's second law can be categorized as: if a resultant force acts on a body, it will cause it to accelerate in the direction of the resultant force. The acceleration of the body will be directly proportional to the resultant force and inversely proportional to the mass of the body. Thus, the mathematical equation can be represented as F equals ma. So Newton's second law is very simple and has three known variables, which is F equals ma. And I've denoted that the force, or the net force, is a vector quantity, and acceleration is also a vector because it has magnitude and direction. So for Newton's second law, F equal to ma, we know that if we had a constant force, right, and say it was 1 Newton, 1 equals ma, and you wanted to relate m to a, it would be a is equal to 1 over m, which means that the acceleration is inversely proportional to 1 over m. So if you have a really big piece of block that you're trying to accelerate, which has a large mass, it means that as the mass increases, the acceleration would decrease, thus mean inversely proportional. And the same as if you had to increase the mass, it would mean if you had to increase the acceleration, the mass would decrease, provided that the force applied to the object under investigation remains constant. For this example, we only have 1 Newton, but it describes the relationship between the acceleration and the mass. So keep that in mind when we start unpacking the next set of examples. Also, what I want you to be aware of is that the force, F, is also directly proportional to the acceleration. So as we increase the force and we push it even harder and longer, the acceleration associated to the block that we're investigating would increase, because we know that the mass that we have attached to it would remain constant. We're not adding mass, we're just adding more force, which would mean it would accelerate faster or slower, thus being F is directly proportional to A. So the first example we're starting off with, assume you have a kilogram box that is placed on a table and a horizontal force of 32 newtons is applied to the box, and the friction force has a magnitude of 7 newtons, and that's between the surface and the box. So the two things we need to try and find out would be to draw a force diagram indicating all the forces acting on the box, and number 2, to calculate the acceleration of the box. Let's begin. So what are we given in this example? They've told us that the box has a mass of 10 kilograms. That's the mass of the box. So knowing that we need to start with Newton's second law, which is F net is equal to the mass times the acceleration. But we know the resultant force, or the net force, is the sum of the forces acting on the box. So the first question that we need to answer is to draw the force diagram labeling all the forces that are acting on the box. So the box that we have, what forces would be acting on it? Well, we know that the 32 Newton force, F applied, is acting on the box. We also know that we've got a friction force between the surface of the table and the box. So that is F friction. We also know because the box is laying on a table, there has to be a normal force acting on it. That would be our normal force. And because it's on Earth, we know that it has a gravitational force, which would be Fg associated with the box. And now we've labeled our force diagram. These are all the forces that are acting on this box. And that's our first question that we've answered, to label all the force diagram components. Correspondingly, we could have also drawn the point mass diagram, which you can convert this object that you're investigating and represent it as a single point mass and still label all the forces on it. You've still got the normal force, you've still got your friction force that is acting on the box, you still have your force applied to the box, and you still have your gravitational force, Fg. Now, referring back to Newton's second law, where F net equals ma, what is the net force that would move this box? It would actually only be the x components, which would be Fg or FFR and the force applied. So the sum of that, F net, is equal to F applied plus FFR. And now we know that F applied is 32 newtons to the left, and I'm assuming that the left-hand side is positive, and the friction force, which is to the right, is negative. And that friction force would be 7 newtons, so it's minus 7 newtons. So my resultant force, or my net force, F net, would be equal to 32 minus 7 is 25 newtons. Remember, F net is a vector, which means you've got magnitude and direction. So F net needs to be to the left. So you found out F net. Great. You know what the mass is because they've given it to you as a 10 kilogram block. Are we able to now find the acceleration of the blocks? Of course we are. So F net is now equal to 25 newtons. So 25 must be equal to, what's the mass of the block? 10 A. So the acceleration of the block would be 2.5 meters per second squared, but you almost forgot, eh? I know sometimes when I was writing exams, I would forget which direction. And remember, this was 25 newtons to the left. So the block also needs to accelerate in the same direction. You can't have a force in that direction and accelerating in another direction. So it's going to be 2.5 meters per second squared to the left. And now you've solved your first simple application of a block moving on a table or a surface using Newton's second law. How easy was that? If you liked it and it was simple enough and you could follow it, I want you to click next. There's another example and more videos for you to follow. Really simple, really easy stuff. We love what you do at Qlicked, and I hope you love what we're doing.